Namaste bachon. Today we are starting a very important topic from Unit 8, electromagnetic waves. We'll understand its core secrets so simply that you will never forget it, and you'll be perfectly ready for your exams. Chalo, let's start with a little mystery.
Just think about it for a second. There's no wire, right? No wire connecting the sun to the earth or your Wi-Fi router to your phone. So how does the signal even travel? It seems like magic, doesn't it? But really, it's pure, beautiful physics.
Well, the answer lies in a beautiful partnership between two fields we already know pretty well.
Now, we've learned these two rules in previous chapters, haven't we? But they always seemed like two completely separate worlds.
So this is where it gets really interesting. How are these two worlds connected? Well, to understand this, let's use a simple analogy, one that will make it stick in your mind forever.
So imagine two dancers on a stage. One is our electric field dancer, and the other is our magnetic field dancer. The key thing to remember is that they are connected. They are not dancing alone. You see, they are in perfect sync. When the electric field dancer moves, it makes the magnetic field dancer move. And guess what? When the magnetic field dancer moves, it makes the electric field dancer move all over again. It's a continuous cycle, a feedback loop. A changing E field creates a B field, and that changing B field creates a new E field, over and over.
In this continuous back-and-forth synchronized dance, it creates a disturbance, a wave that travels outwards. It's a self-sustaining wave. The dancers themselves aren't running across the stage, but the wave they create does. And that, Bacho, that traveling disturbance is our electromagnetic wave.
Okay, so now let's see how this beautiful idea was finally pieced together and how it led to one of the most elegant concepts in all of physics.
And the genius who saw this complete picture, the full dance, was this man, James Clerk Maxwell. He realized the symmetry was absolutely perfect. While others only saw the individual steps, he saw the entire performance. So what was Maxwell's great insight? He proposed the missing piece of the puzzle. We already knew from Faraday that a changing magnetic field creates an electric field. Maxwell said, for the universe to be symmetrical, a changing electric field must also create a magnetic field. And that completed the circle.
Okay, so this brings us to the crucial NCERT definition. Please, Bacho, you must remember this for your exams. It says, electromagnetic waves are coupled, time-varying electric and magnetic fields that propagate in space. Now, what are the key words here? Coupled, that means they are linked together like our dancers. And time-varying, that just means they are constantly changing, oscillating. Simple, right?
So this is what that dance actually looks like. You have the electric field oscillating in one plane, say up and down. Then you have the magnetic field oscillating in a plane perpendicular to it, maybe in and out. And the wave itself, it travels forward, perpendicular to both of them. All three, the E field, the B field, and the direction of travel are mutually perpendicular. This is a classic example of a transverse wave.
You know what's amazing? All these waves, it doesn't matter if it's a radio wave, a microwave, or visible light, they all follow this one simple fundamental rule. C equals F times lambda. That is, the speed of light is just the frequency multiplied by the wavelength, a very important formula to remember.
Let's take a tiny worked example, just to see how easy this is. Let's say a radio station, one of your favorite FM channels, broadcasts at a frequency of 100 megahertz. So can we find out its wavelength? Well, it's simple. We just rearrange our formula. We know wavelength, lambda, is equal to the speed of light, c, divided by the frequency, f. So we just plug in the numbers. For c, we use 3 into 10 to the power of 8 meters per second, and for f, 100 megahertz is just 100 into 10 to the power of 6 hertz.
And when you do the math, you get a very simple answer, 3 meters. So the radio waves from that station have a wavelength of 3 meters. Just imagine that. The distance between one wave peak and the next is about 3 meters. That's huge. Is this point clear? Very good.
Now, this is very important. Let's talk about some silent killers. These are common mistakes that students often make in exams, which can cost you valuable marks. So please, pay close attention here.
Okay, mistake number 1. A lot of students think that EM waves need a medium to travel, like sound needs air. This is completely wrong. Remember sunlight? It travels from the stars through the vacuum of empty space to reach us. So EM waves do not need a medium. In fact, they travel fastest in a vacuum. And the second big mistake? Thinking that the electric and magnetic fields are two separate things. No! Remember our dancers? They are two sides of the same coin, two inseparable aspects of a single phenomenon called electromagnetism.
So let's zoom out for a second. What is the big picture here? Why is this idea so important? Why do we call it a grand unification?
You have to understand, before Maxwell, these three fields of physics were studied as completely separate, unrelated subjects. People had no idea they were connected.
What were these fields? Electricity, magnetism, and optics, which is the study of light. And then Maxwell came along, and his equations proved beautifully that all three are just different manifestations of a single underlying force, electromagnetism. This was absolutely revolutionary, a true grand unification in science.
Okay, so for your revision, let's quickly summarize the key takeaways. Please make a note of these. First, an accelerating charge is the source of electromagnetic waves. Second, the E and B fields oscillate perpendicular to each other and perpendicular to the direction of propagation. Third, the speed of EM waves in a vacuum is a universal constant, c, which is about 3 × 10⁸ meters per second. And finally, they carry energy and do not need a medium to travel. These are the absolute essentials you must know.
And to leave you with a final thought, just think about this question. We said that an accelerating charge is the source of these waves, right? And light is an electromagnetic wave. So, does that mean we can create light just by taking a charged particle like an electron and shaking it? It's a fascinating question, and we'll explore the answer in the next part of our chapter.